Chapter 3, the bonding theory. The bonding theory, we have several theories. We will start first with the theory of Lewis that draw the valence electrons in a molecule. Why we draw the valence electrons? Since we know that the valence electrons are responsible for the bonding. This is a theory. Then we pass from the Lewis theory to another theory, which is the valent bond theory. And we pass from one to another theory since we have inconvenience. Then in the VBT, the valence bond theory, we will explain this theory in details. What are the interests? What are the inconvenience? Then we have to pass to another theory, which is the MOT, the molecular orbital theory. So we have in the bonding theories, we have three types. We have LT, which is Lewis theory. Then we pass to VBT, which is the valence bond theory. Then we pass to MOT, which is the molecular orbital theory. So the aim of the bonding theories is to explain how and why atoms attach together. The bonding theories also explain why some combinations of atoms are stable and others are not. For example, if we consider water, the molecular formula of water is H2O. That means the oxygen is bound to two hydrogen, so we have two bound OH. The question, why the molecular formula of H2O is not HO, for example, nor H3O. So to explain the presence of this molecular formula, we use the bonding theories. So one of the simplest bonding theories was developed by Lewis and is called the Lewis theory, and the abbreviation is LT. The Lewis theory draw the valence electrons or use the valence electrons of the atoms to explain the principle of bonding. In each atom, we have a nucleus. Around we have core electrons, and at the end we have valence electrons. We are not interested about the core electrons since they are not responsible for the bonding. The valence electrons are responsible for bonding between two atoms. So in order to explain this bond, we draw the valence electrons of the first and the valence electrons of the second. So using Lewis theory, we can draw models called the Lewis structures that allow us to predict many properties of the molecule. And pay attention, we have to make difference between Lewis structure and the geometry of the molecule. The Lewis structure is the drawing of the valence electrons of the atoms in a molecule. We can use this structure in order to find the geometry, but the Lewis structure is not the geometry. So what are the properties of the molecule we are interested? For example, the molecular stability, the shape, the size, and the polarity, and we will talk about these properties at the end of the chapter. So why do atoms bond? Atoms form chemical bonds to make their outer electron shells more stable. For example, in case of H2O, the oxygen is in group 6 or column 16. So the oxygen has 6 valence electrons, and the electronic configuration ends by S2P4. And as we said, the most stable state for P4 is P6, which is completely filled. So the oxygen tends to be more stable. In other words, the oxygen tends to get 2 electrons from outside atoms. For this reason, we will have bond between oxygen and hydrogen, for example, and another hydrogen that will generate 2 electrons to oxygen in addition, and in this case, the oxygen in H2O molecule has orbitals completely filled, so this oxygen is stable. In case of sodium, the electronic configuration is Ne, neon, 10 electron score, 3s1. So the sodium in this electron, according to this electronic configuration, should gain 7 electrons in order to have the orbitals on shell 3 completely filled, or the sodium should lose 1 electron. So it's easier for sodium to lose this electron than to gain 7 electrons. So the sodium will donate an electron to another that need electrons. So the electron is transferred completely from sodium to another atom that need electrons. For example, consider Cl. Cl has orbital s2 p5. So it needs 1 more electron to be stable. In this case, we will have bond between Na that lose this electron on 3s1 to the orbital p5 of Cl, and the bond is called, in this case, ionic bond. So the ionic bond is a bond between an atom that need to release electron to donate and another atom that need to gain electrons. So this is a bond between a metal like Na and non-metal like Cl. The second type of the bond is the covalent bond. And this is a bond between 2 atoms that needs electrons. For example, consider oxygen and Cl. The oxygen needs 2 electrons, and the Cl needs 1 electron. So oxygen could not give electrons to Cl, and Cl, by the same way, could not give electrons to oxygen, since the 2 atoms needs electrons. So in this case, they will share the electrons between them, and the bond is called covalent bond. So a covalent bond is a bond between 2 atoms that needs electrons. So it's a bond between 2 nonmetals like oxygen and Cl. We have other types of bond which is not ionic, 100% ionic, nor 100% covalent. And this type is called the polar bond. What is the meaning of polar bond? Is an intermediate bond between covalent and ionic. So it's not ionic 100%, nor covalent 100%. It has a percent of ionic character and covalent character at the same time. So we have to calculate in the next slides what is the percent of covalent and ionic for a polar bond. Bonding at the microscopic scale. Consider, for example, the table salt. The table salt is NaCl, and NaCl is powders. So at the microscopic scale, we can identify these powders, so we can see that we have a compound between Na and Cl. So this is at the macroscopic scale. What is the type of bonding, or what happens at the microscopic scale? A chemical bond forms when the potential energy of the bonded atoms is less than the potential energy of separate atoms. For example, consider Na and Cl, and they have to do bond. So at the macroscopic scale, they will be close, and when they will be close, so we have attractions between electrons of the first and the protons of the second, protons of the first and electrons of the second. So the two atoms will be close due to the attraction. But at the same time, when the atoms are close, we will have repulsion between the electrons of the first and the electrons of the second, the protons of the first and the protons of the second. So when the atoms are close, we have two types of interactions. We have attraction and we have repulsion. If the repulsion is greater than the attraction, so these two atoms could not be joined together. And if the attraction is greater than the repulsion, so we will have a bond between the atoms. So the energy, when we have repulsion, the potential energy is maximum. As the two atoms are close together, the potential energy decreases till the attraction of the two atoms. So at this stage, we will have formation of bond. In other words, if the attraction is greater than repulsion, so the most stable is the formation of the bond. In this bond, as I said, we have to consider the nucleus repulsion. This is positive repulsion. We have to consider the electron repulsion. This is negative repulsion, and the nucleus to electron attraction. So we have three types of interaction. Then we do the balance. If the nucleus to electron attraction is greater than repulsions, so we will have a bond. The types of bond we know are four types. First, we have ionic bond, and this is a bond between a metal and non-metal, and the electron is completely transferred from metal to non-metal. The second is the covalent bond. This is a bond between non-metal and non-metal, and the electrons are shared between these two non-metals. And we have the third type, which is not 100% ionic, nor 100% covalent, which is ionic covalent bond. We call polar covalent bond or polar bond, which has percent ionic and percent covalent. And the fourth type is the metallic bond, which is a bond between metal and metal and the electrons are cooled between. Electronegativity. In the periodic table, in the trends of the periodic table, we talk about several properties of elements: the atomic size, the ionization energy, and the electron affinity. Now we have another property, which is the electronegativity. And pay attention, we have difference between the electronegativity and the electron affinity. So what is the definition of the electronegativity? The electronegativity of an element is its capacity or its ability to attract electrons to itself in a bond. In this figure, we have a bond between two animals. Okay? The first has the ability to attract the electron to itself greater than the second, since the first is stronger. By the same way, if I have two atoms A and B, A has electronegativity and B has another electronegativity. If the electronegativity of B is greater than the electronegativity of A, so the electrons bonding between A and B are more attracted to B, which has greater electronegativity. So the electronegativity is the capacity to attract electron to atom in a bond. What is the trend of electronegativity in a periodic table? In the periodic table, the general trend, the electronegativity increase from left to right, from down to up. So the electronegativity increase by the same way of, for example, the ionization energy, and in the opposite direction of the radius. So the electronegativity increase across period from left to right. It decrease down group from top to bottom, or it increases from down to up. F is the most electronegative element in the periodic table. Francium is the least electronegative element. Noble gas atom are not assigned value because the noble gas did not form a bond, so we don't talk about electronegativity. And the electronegativity is very important in order to understand the type of bond AB. For this reason, we have common values of, or we have common trend. In order to find the type of bond, we have to look for the difference of electronegativity between atom A and B that constitute this bond. As you observe, F had the greatest electronegativity, then oxygen, then Cl, then nitrogen, then Br, then I, S, carbon, At, phosphorus, hydrogen. So we can read this rule as Falkland-Brice-Kapsch. Falkland-Brice catch. So F is more electronegative than oxygen, more electronegative than Cl, more electronegative than N. This is Falkland. Br greater than I, greater than S, greater than carbon, or Br greater than I, greater. So this is a brace. Carbon greater than At, greater than P, greater than hydrogen. So catch. This is the Falkland brace catch notation that make easier the comparing of the electronegativity of elements without using the periodic table. Falkland, never forget, Falkland brace catch. So as I said, the electronegativity of element is very important in order to predict the type of bond. So for a bond AB, the type of the bond depends on the electronegativity difference between A and B. If the difference between A and B, noted delta difference, En, electronegativity, or simply XAB, if the difference is between 0 and 0.5, the bond is covalent. And if the difference is between 0.5 and 2, so the bond is polar covalent. If the difference of electronegativity between A and B is between 2 and 4, the bond is ionic. So between 0 and 0.5, it can be equal to 0.5 here. In the polar covalent, it starts 0.51, for example, or 501, and 2. It can be equal to 2 in the polar covalent. The difference of electronegativity is greater than 2 and can be equal to 4, so the bond is ionic. As a conclusion, to know the type of bond, polar, covalent, or the intermediate bond between ionic and covalent that we call the polar covalent, we have to calculate the difference of electronegativity between A and B. And to find the electronegativity of A and B, we have to use the periodic table to follow the general trends. Or it's easier to use directly the rule of Falkland brace catch if these atoms belong to these bonds. And to note, in case of the polar covalent bond, so the difference is between 0.5 and 2. When the difference of the electronegativity is low, tend to be 0.5, so the bond is less ionic, or the bond is less covalent. And if the difference tend to value 2, so the bond is more polar. For example, suppose you have a bond of difference of electronegativity delta En1 and another bond of delta En 1.5. The bond with delta En 1.5 is more ionic than the first, or we can say the bond is more polar than the first. Or we can say the first is more covalent than the second, or the first is less polar than the second. So as we approach to the 0.5, the covalent character increase. As we approach to 2, the polar covalent or the ionic covalent or the ionic character will increase. So in the polar bond, or the polar covalent bond, we have a percent covalent and percent ionic. Consider the bond HCl. The hydrogen has electronegativity 2.1 and the Cl has the electronegativity 3. So the difference of electronegativity delta En between Cl and hydrogen is equal to 0.5 to 0.9. And this value is between 0.5 and 2. So the bond HCl is polar bond, or the bond HCl is polar covalent bond. That means HCl is not 100% ionic nor 100% covalent. The bond has percent covalent and percent ionic. Cl is more electronegative than hydrogen. First of all, I have to explain what does mean this for. The hydrogen has one electron valence. So the hydrogen, this electron, has a probability of presence of points. In the Cl, we have 7 valence electrons. So we have also probability of presence of these 7 electrons. And when H is bound to Cl, so the bonding electrons between H and Cl will also be in a certain place where the probability to find this bonding electrons is maximum. So this is a representation of probability of presence of electrons in the molecule HCl. I return to the bond HCl. Cl is more electronegative than hydrogen. What is the meaning of Cl more electronegative than hydrogen? First of all, the hydrogen has 1 valence. Cl has 7 valence. So H will share this electron, or will share its electron with Cl. And the electrons sharing are in the distance between H and Cl, or are in the space between H and Cl. Since Cl is more electronegative, so the Cl will attract the electrons to itself greater than hydrogen. So the bonding electrons are close to Cl and not close to hydrogen. Cl attract the electron to itself. So the Cl will have density, will have greater density of electrons around it. So the Cl will have a partial charge delta minus. And when the electrons are close to Cl, so the hydrogen that have 1 proton will have therefore delta plus charge. The partial charge describes the electron density around the atom. Cl is more electronegative than hydrogen, so the Cl will attract the electron to itself. The electron density around Cl is greater, so Cl will have a partial charge delta minus. The hydrogen will have a partial charge delta plus. Delta minus and delta plus will create the dipole moment of the bond. So the dipole moment of a bond is due to the presence of partial charge delta minus and delta plus around atoms. So what is the dipole moment by definition? The dipole, the bond dipole of the bond AB is by definition, is by convention, is a parallel vector to the bond directed from the positive pole to the negative. Directed from the positive to the negative. So in case of HCl, the bond dipole will be directed from hydrogen to Cl, since hydrogen has delta plus and Cl has delta minus. So the bond dipole of a bond AB is due to the difference of electronegativity between A and B that release a partial charges delta minus and delta plus. So by convention, we draw it as a vector parallel to the bond directed from the positive to the negative. And this vector is noted mu. Mu means bond dipole. What is the intensity of the bond dipole? The direction, as we said, is a vector parallel to the bond directed from the positive to the negative, and look, we put plus at the beginning of the vector. So what is the intensity of the bond dipole AB? Mu AB by definition is equal to the absolute value of the charge, this delta, minus is equal to delta plus in absolute value. So it's equal to absolute value of delta, which is the partial charge, times the distance between the two atoms. So mu AB equal absolute value delta times dAB. Mu AB is the bond dipole of the bond AB. Delta is the partial charge in Coulomb, and dAB is the bond distance in meter. So mu AB is in Coulomb times meter. Or we use another unit, which is the unit of dBi that discover the bond dipole, noted D. 1 dBi equal 3.33 times 10 minus 30 Coulomb times meter.